Hi everyone, I'm Herbert from MetaSecure Labs. Today my topic is how to build a more secure and trustworthy Web3 infrastructure. As Aptos is everybody knows is very critical infrastructure layer one in this Web3 world. So we're gonna go through some details about some implementation and in design details about problems and issues in various infrastructure code and design, and then we're going to propose some of the our recommendations in how to build a secure infrastructure. This is my background. I used to work at different security companies, and also I build security solutions for cloud infrastructure like IBM Research and also ByteDance US AI Lab. I also founded my previous company in the cloud native space, basically focusing on security perspective of cloud native infrastructures. And then I'm working as a full professor at the University of Chinese Academy of Science in computer science and security area. There are scientists from our group actually building tools that identify critical issues and bugs for various type of infrastructure, like Ethereum Foundation actually give us some grants previously. We help them identify hundreds of bugs. And also Web3 Foundation also gave us some grants. We're actually focusing on most of the popular infrastructure languages like Rust language and also the Go language to providing tooling, security venting toolings to help them identify critical issues and bugs. And we recently actually identified several issues in the Aptos Rust implementation. This is one of the issues that we submitted on the Aptos like official website in their move languages. And today I'm gonna start with this. And ironically, there's another company actually do the manual auditing for Aptos, and they identify 7 informational issues from the readout. So it's quite like a different readout eventually. The case that we find for Aptos that actually have been reported and confirmed by their developer on their website is a crucial deadlock in one of the move languages component. Their developer actually confirmed the bug as soon as we submitted, and then they mentioned it's a very good catch and thanks for putting this up and for the fix. And it looks awesome that our techniques can identify this very critical issues. This type of deadlock is actually very hard to test in the real-time code review process, and also it could be very easily found by our automated deadlock detectors. So the bug actually coming from in the move runtime. Basically, let me explain a bit about loader, which is responsible for loading the scripts and relevant modules. So, and then it can hold the cache of all the loaded entities. So the module cache, in this loader is protected by a rewrite log. Basically, it's a very basic programming primitives to provide some of the concurrency properties and also some of the runtime behavior guarantee. Unfortunately, one of the misuse in this space actually can potentially lead to a falling deadlock about these primitives. It's actually happened in this loaders method called transitive depth closure. In this process, the Aptos move actually try to acquire the read log on module cache before a recursive invocation on top of it. So the first step is acquire the read log, and then it locked the whole space. The scope is actually a little bit large, and it come into a transitive call into this transitive depth closure, and then it will recursively call another times of the potential read log. However, in between, there could be some interleaving with some other read or write log on top of it that can causing a potential deadlock issues when multi-threading are happening. So a deadlock example in this could be explained in this way. So given there are like two threads here, so a recursive read logs could potentially interleaved by a write log. So then it could lead to deadlock. So let's go into some more details. For the thread 1, when it comes into the function called transitive dep closure, it's first going to invoke the module cache read log the first time for the first read log acquisition. And then given there's another thread in the function flush it invalidated. It's actually called a write log on top of the same resources, and it's actually waiting for the release of the first read log. However, in the meanwhile, if the thread 1 is keep on continuing do a recursive call on the read log again, this read log will actually then wait for the release of the write log. Then this three basic operations actually waiting for each other and forming a circle, resource dependencies among each other that causing leads to a deadlock, obviously. So we can see that usually in the development process, it's quite difficult for different developers and with different contexts to identify all these cases, and auditing won't help because it should be catched in the automated fashion, given so many of like different languages, status and cases. So we're actually providing full security checking of this type of bugs in Rust and Go languages to help the ecosystem build up more secure infrastructure. So the fix by our suggestion is actually try to reduce the scope of the log. Basically, try to move the read log a little bit within a smaller scope so that it can prevent the interleaved resource acquisition from different threads. And also, very interestingly, there are some other like infrastructure happening some hacks recently in the wild fashion. Like very recent, there's a BNB bridge hack, which is also caused by a implementation detail issues that were not found in ahead of time, like in a shift left fashion. However, will be actually by the hacker leveraged and causing a lot of money being tokens being stolen in the cross chain, like a scenario. Let's give some background here. The Binance chain was actually hacked almost 600 million of asset value. And then roughly 100 million, 90 million has been moved out of this ecosystem. So the exploit is rooted very deeply, actually very interesting, from the Cosmos chain library, which is heavily used by other like infrastructure builders. I'll show later for some cases. This is one of the details, like we can see, like in October the 6th, I think about like roughly 2 weeks ago. In the afternoon, the hackers will start like some block height at 219.559.68. Then by calling a particular contract to pay 100 BNB as a test, and then later up to 2 hours is gonna actually transfer like 1 million tokens based on the BNB like token hub contract. And right after like almost 3 hours, 2 to 3 hours, they do another like big transaction by obtaining like another 2 million like coins. So we can see that the process of doing the transaction are quite fast. So you in these cases you have two ways of preventing this type of problem. The first is you do a better design, a more secure like infrastructure design, and then you do like more automated scanning and implementation protection on the implementation code. And the third is you try to provide some more of the real-time detection and anomaly prevention systems on top of the bridges in order to prevent this type of hacks. Because it's happening so fast, once it's been exploited and triggered, it's very difficult to trace back most of the losses. And the root cause actually, as I mentioned before, is in some of the interesting cases, like the relayers will actually initialized a transaction to this BNB chain cross-chain contract. It's actually calling a function called handle package. The main parameters are the payload and the relevant proofs. So the cross-chain contract actually verify the validity of the payload according to a Merkle proof. And then it's actually based on the implementation of the IVAL tree verification process. This tree is actually a variant of the AVL tree that is an implementation of the tree provided by verifiable roots for key values. And then the payload is, if the payload is valid, then it's gonna be passed into a message and sent to the token hub contract to process the message. Then the token hub contract handles the message byte and the receiver receives the specified number of tokens to a particular address. Then the stolen of the token can potentially happen. So in this attack, the attacker actually sent an invalid payload that actually forges proof, which passes Merkle proof validation process in the previous step 2, and then successfully stealing millions of money funds from this token hub contract. So attacker forged the proof by add a malicious leaf node to the range proof of IAVL tree, and while the forgery does not cause the calculation result of this Merkle proof to change, which means it's actually a very shallow implementation detail of a missed type of check. When the Merkle tree is not a full tree, then can cause potentially a mischeck of the Merkle root. So that can that can actually be leveraged by the attacker to manipulate the payload details in the verification process. So here you see the example in the function like proof in the proof IVAL value .go implementation details. We can see that the root only are relevant to the hash of the leftmost leaf nodes of this tree and its relevant passes, which means in this proof creation and validation process, an inconsistency could be inserted by the malicious node in order to manipulate the payload result and then helping the adversary to transfer a certain number of values out of the ecosystem. So we can see that potentially a very small implementation details of the Cosmos library could raising such a big issue. And we identified that this type of implementation used at almost like 20 projects in the ecosystem, which actually already been reported by our dependency analysis toolings. And besides implementation detail, the current infrastructure could also facing some of the design problems. Very recently, there was researchers proposing DK bridges that try to link like two public chains while using some of the DK relevant technologies. First of all, in this detailed implementation, you actually retrieve block headers from the sender's chain, and then you try to verify this block header from the sender and generate a ZK proof on top of it of this block header of the sender's block header, and then the receiver chain C2 actually verify the DQ proof and are gonna be accepting the block header. The application that receiving this on the receiver chain can then perform like different type of verification over the block header, and then to either like mint some token or provide some liquidity on top of it. So the DK proof here seems like more secure and also providing a more succinct size of the commitment and proof, so that the process can save gases on the transaction. However, there could be some potential issues if it's not interesting, not like very carefully designed. We can see that in this token transferring process. So, for example, given the case Alice wants to transfer X tokens from chain number 1 to chain number 2, so there's like a pair of methods that are very critical. One is the burning process transaction of the smart contract, and although the other is the minting process of the operation on this smart contract of the target chain. So only when the chain 2 confirms there's X amount of tokens that are indeed burned on chain 1, that it gonna means on chain 2. However, if not carefully designed, there could be potential attacks that can leveraged, vulnerability that can be leveraged by the attackers. For instance, in this relay network, if someone tries to transfer, for example, 10K tokens from address 1 to address 2, however, if it only has 10 tokens, how it gonna looks like usually in a normal fashion. So the scenario that without a particular attacking, basically in this general like normal situation, the phase 1 is gonna burn like 10K tokens on chain 1, and then the code execution would potentially be reverted. Is because it only has like 10 tokens, so the account address 1. Basically, the value did not change on top of it. So the phase number 2, basically it will send the header of the mint blocks and the relevant ZK proofs to chain 2. In the phase 3, the chain 2, when they validates the ZK proof and check the block headers, it actually won't go through, because it's checked whether there's certain event of transferring a particular number of like 10K tokens under the particular address. So then it won't mint, the check will fail, then it won't mint this tokens on top of it. However, in this process of a relay network in the between, there could be malicious forking of fabrics of this block header from the relayer. Because it's only a header, it can try to remove some of the validation process from the smart contract in the burning method, and then it could include some transaction code, like for example burn like 10K tokens in its own created malicious block, and then when it executes a modified like result, then the magic could happen, because there's actually no validation process to actually check where the transaction actually happened, and whether the block header is a legitimate one or it's from a malicious relay network, some malicious node in the relay network. So on the step 4, could potentially still mint a block with 10K tokens on top of it that can create inconsistency states between the source and the destination chain. So this is make it like quite a challenging task to building a kind of like design very solid and secure infrastructure, given there are certain pre-assumptions you have to hold. For instance, any state changes on the source chain, you have to confirm that it can be successfully recorded, and there wasn't the origin of the attacks, and also the hacks could come from like various design flaws. For instance, if the verification process only include the headers, and it's like a proof of work one, and then you can potentially create like fake headers, and then will produce some like false transactions, and making the minting process happening. So and after this happened, there's no way you can trace back, because everything looks like quite normal afterwards. Even you use like ZK proof technology to further verify the created circuits, it's just like you're working on proving some of the already like vulnerable designs and the results. So everything gonna go through smoothly, as normal as it looks like. So this is how potentially looks benign and looks strong like design could still be exploited and leveraged by sophisticated hackers, given the protocol in between could be very like interesting and very like complicated to play with. So I think in order to providing like more solid design and implementation, so people have to come from different perspectives. First is from the design phase, you have to reuse some of the cryptographically secure manner in order to improve the whole overall design, and then try to give like a shrinked attack surface design, which means you should not expose too much of the status to the outside. And the other thing is, when you do detailed implementation, you need to use some of the existing protocols that has been validated for years. You should not rather like go from like scratch and build your own crypto mechanism or crypto protocols, because those are not like formally verified, and usually are vulnerable to corner cases and issues. And the other thing is to do some verification process, and also for instance, for critical portion, you should do like formal verification, and also some of the code analysis based on some automated tools, and in order to prevent the implementation detail that can causing security bugs and vulnerabilities. So in our case, we actually providing a better design of different infrastructure and suggestions of those, and we also do automated scanning of various smart contract and also infrastructure code. In terms of the Move ecosystem, we're gonna build like more secure bridges, and on top of it, we will have like smart contract security checkers to automate checking various type of issues. And for the infrastructure part, we also providing shift left tools for the CI/CD pipeline in order to scan, for instance, the Rust and the Go implementation of different infrastructures, in order to make sure that most of the common and existing vulnerabilities could be covered. And here is one of the example of our SaaS platform, which we'll share to the community for use. People can submit like different smart contract or other like code given the URL or address. Then our platform gonna scan through like existing vulnerabilities and then existing hacks on top of it, in order to identify most of the cases that are well known. And the results are quite usually coming quite quickly, because we are doing like a lot of optimizations on top of the pattern matchings based on our machine learning and some of the AI algorithms on the back end. Yeah, this is pretty much our our design cases for it. Yeah, that's pretty much the overall talks that I want to give for all of you. And this is my Twitter ID. We're actually a bunch of researchers working on building secure infrastructure and helping the Web3 community building more like secure and robust infrastructure. In terms of the Move ecosystem, later we're gonna providing like security scanning for the smart contract in Move languages, and also we're gonna providing infrastructures like secure bridges and other more mission critical infrastructure on top of the ecosystem in order to help the user and also developers to build a more secure like Web3 systems and cases. So please feel free to drop me email or connect me through the Twitter in order to get more details about our toolings, about the service that we provide, and also we will providing APIs to the community that can be freely used in order to test their smart contract, their implementation languages in Go and Rust for the infrastructure and other details. So yeah, thank you so much for your time, and then please come by and then drop me emails and messages. Thank you so much.